Alright, so in this video, my nerds, we're going to go over some organic chemistry questions and sort of go through how to do them. So buckle up, let's have a look, let's see how we go. So our first question here is about making and diluting solutions. So we start with calculate the mass of the sodium sulfate you would weigh out to prepare a 50 milliliter solution, or 0.050 liters, of a 0.15 moles per liter solution. This means that's how many moles are diluted into every liter. We like to use moles because it's one that gives us consistent ratios when we're talking about chemical reactions and equations. We can see here that I've put the tiles up from the periodic table to give us the information. Another thing we can see is that our piece of data with the lowest amount of significant figures is moles per liter, and that's 0.15. So there are two significant figures, so that means our answer can be no better than two significant figures as we move on. So these are our key facts. We've got 50 milliliters, or 0.050 liters, actually 0.0500 liters. We have 0.15 moles per liter of the solution, and it is of sodium sulfate. So first off, let's have a look. So we've got the sodium ion and the sulfate ion. That's the first thing it's asking us to know. The next thing it's asking us to know is how to put those together. For example, this is what it looks like. We do a little dropover method here where this 2 becomes how many sodium ions, this 1 becomes how many sulfate ions, and if it was like, say, 4 to 2, we'd, shrink it down, simplify it down. So it's 2 to 1, so 2 sodiums, 1 sulfur, 4 oxygens, or 2 sodiums, 1 sulfate. So the first thing we know is, how do we work out the concentration? We've already got the concentration there, but we kind of have to backwards map this question a little bit. So our formula for concentration is concentration equals moles divided by volume. Okay, so this little N symbol means moles, V equals volume, and C is concentration. Actually, one of the important things I've left off here is it's asking us for the mass, not the moles. We still have to use this equation, but it's asking us for the mass. So our concentration is 0.15. That's a known. 0.5050 should be an extra 0 there. Liters, doesn't matter, but that's there. That's a known. Our unknown here is the moles. So this means we're going to have to rearrange this equation, right? So we rearrange it to get the N on its own. So that's this V here, is the volume here is divided by, so it's moles divided by volume. So to get rid of that, we must multiply it by volume, and that would cancel those two out. But that means we have to do the same thing on the other side of the equation, which gives us to C times volume. So moles equals C times volume. So we end up with 0.15 moles per liter times 0.050 liters, which gives us 0.0075 moles. Now, I've not rounded down or up on anything. You don't need to with this one, but you'll see this later on. So I want you to make sure that you don't round up or down until the very end. So then we go here. So our sort of little statement to start off with is that 0.0075 moles of sodium sulfate was dissolved into 0.050 liters to make a 0.15 mole per liter solution. All right, we still haven't used any of this info. This is about to come up. So we want to know what the mass is. So our equation for moles that involves mass is moles equals mass divided by molar mass. Okay, so moles equals something in grams divided by grams per mole. That cancels out the mole, the grams, and gives us just the moles. But we can rearrange that to give us our mass, which then becomes mass equals moles times molar mass. Same as we did over here. We rearrange this volume. If we want to do it on this side, we've got to do it to the other. Here we rearrange the molar mass. We want to rearrange it to this side. So we get the mass on its own, so we need to multiply it, which means we need to multiply it over here. And then we can just substitute in our values. So 0.075, that's the moles from over here. If we want to put the molar mass in, that means we put these numbers for however many atoms there are. So there are 2 sodium atoms in this formula over here. 2 sodium atoms, which means it's 2 times 22.990. We have what's that? 1 sulfur, so plus 32.066. That's the molar mass of sulfur. Plus 4 times, because that little 4 there, 4 times the molar mass of oxygen, which is 16.999. This is a little aggressive. It's very rare that you'll see oxygen as anything other than 16.0. Speaking of aggressive, you can hear the cats going mental in the background. So that becomes 0.0075 moles times 142.06 grams per mole. That's pretty small, actually. Like not the number, the way I've written it there. Which gives us 1.065045 grams. Now, again, there's a much more accurate number than we have, so we need to cut that back to the correct number of significant figures, which is 2. So that gives us 1.1 grams. So when we're making up this solution in 50 milliliters, we put 1.1 grams in, and then we add our water up to 50 milliliters and shake it away. So therefore, I'm having a cat fight in the corner. Therefore, 1.1 gram of sodium sulfate is dissolved into 0.050 liters of water to make a 0.15 moles per liter solution. I like to always put in an answer statement. It removes all ambiguity. Like when they say show working in a question, this is your answer. This is your working out. Okay? So we want an answer statement. Now, because chemistry teachers are always the best or the worst, however you look at it, there's always a part B to your problem. And in this case, it is what volume of this solution would you need to dilute to prepare a 125 milliliter solution of 0.05 moles per liter. This is actually, I love these. These are one of my favorite types of questions in chemistry is the dilution questions. Because I like doing serial dilutions. Doesn't matter. Anyway, so what it's asking you is this purple here, this is your original solution. So it's asking you, how much of the original solution do you need to put in to make up 125 milliliters of 0.05 moles per liter solution? Okay, so we've got an original solution of 0.15. We want to make it 0.05, but we also want 125 milliliters. So this is actually really useful in the lab situation, which is why I kind of like this one. So we write this equation as this. It's C1V1, so concentration 1 and times volume 1 equals C2V2. Okay, so basically it comes out as a nice little ratio. So, for example, our concentration 2, so the one that we wanted to end up is 0.05 moles per liter. Our volume 2 is we want it to be 0.125 liters. Our concentration is our starting concentration up here of 0.15, and we want to know what volume we put in originally, and then add water up to that 125 milliliters. So let's pump our numbers in that we know. We've got 0.15 times V1 equals 0.05 times 0.125. So then we rearrange our equation. We do this a lot in chemistry, and these equations make our ideas really flexible. So we can take this 0.15, divide it away from there, which means we've got to divide it on this side. So it becomes 0.05 times 0.125 divided by overall 0.15. And that gives us this solution here, this volume. So we want to put 0.0416666666, it's a bit satanic at the end there, liters. Now that's obviously more accurate than we have. So look at our significant figures, and we'll do this to 2 significant figures. And that gives us 0.042 liters. So we take 0.042 liters, 0.042 liters of the original solution, put it into our Erlenmeyer or conical flask, and then we add enough to make it up to 125 milliliters. Actually, you wouldn't do it with a conical flask. You'd do it with a volumetric flask, but I couldn't draw one, so that's what we get. So therefore, our 0.042 liters or 42 milliliters of the original solution is diluted to 125 milliliters of 0.05 moles per liter solution. So again, working out answer. Let's have a look at some combustion of organic compounds. Good types of questions. We've got hexane. Hexane is cool. It's going to burn. It's going to burn completely. So the first thing it's asking you to do 2 things. It's asking you for the balanced equation. So you have to know what the reactants and the products are, and it's asking you for the states. The states is a sneaky, tricky one there. I'll show you why. So here is our equation unbalanced, right? C6H14, that's hexane, plus O2, oxygen gas, always oxygen gas, goes to completion. Does not write equals, right? Goes to completion to give you carbon dioxide and water vapor. Now, for any organic compound that is burning completely, these are your products every time. It's when it's not burning completely we start to get other stuff, but this is asking for burning completely, which means there's enough oxygen there for it to combust. So a balanced equation, let's do that first. I like to draw a little table down here, and on the reactant side we have 6 carbons, 4 hydrogens, 2 oxygens. On a product side we have 1 carbon, 2 hydrogens, 3 oxygens. Now hydrogens are the easiest ones to deal with first because they're the simplest and there's heaps of them. In this case, so there's 14 hydrogens over this side. We could multiply this one by 7, yeah? And that would even up our hydrogens. Except, slight problem, there's this little oxygen on the end. And we'll see that our oxygens over here have an even number. So we want to keep that to be an even number. So instead of going 7, we go to 14. This is a little bit trial and error. I've got another video with a set of rules on how to do this, and I'll link that down below. But yeah. In fact, I've got videos for how to do all these separate steps, and I'll link put all of them in the description below. Anyway, so we go to 14, so then we go double that here, so we now have 28 hydrogens on this side, and 16 oxygens, gold. So we can double that over here, this sort of hexane, and that now gives us 12 carbons, but carbon's easy to deal with because it's over here, and 28 hydrogens, so our hydrogens match out. Now next, we put a 12 at the front of this one to even up our carbons. We now have 12 carbons. Okay, they match. But we now have 38 oxygens. That's a lot of oxygen. So we've got 24 oxygens here plus 14 oxygens there. That gives us 38. So we need to now do something with our oxygens because that's the only one that's not matched up. But you can see we left oxygen till last because it's all over here on its lonesome, and we can solve that out. So we put a 19 at the front, boom, 38. And we've now got a balanced equation. We don't have our states on there though. So what makes the states a tricky one is that when we burn something, it's a gas. We can only set gases on fire. It's weird to think about. Like when you're burning, say, paper, it's not the solid paper you're burning. It is the paper vapors, which is why everything has to be heated up before it catches on fire, right? So you can't just throw a log on a fire and try and heat it up set it on fire with a match, right? You got to heat the whole log up before that wood will start to vaporize on top. Just the surface layers will vaporize and that will catch on fire. So hexane, which is pretty volatile, will be a liquid when you're dealing with it usually, but when we set it on fire, we bring a flame near it, or it heats up a little bit in the presence of oxygen. And once it turns into that gas stage and it goes over the heat of ignition, it's able to catch on fire. So that makes sense. So our hexane is a liquid. Everything's a liquid when it burns. Sorry, a gas. Everything's a gas when it burns. Our oxygen is a gas because it's always a gas, as is our carbon dioxide. But our water, it's fire, right? So this water isn't water, it's steam. It's water vapor. So that's why that one's always a gas as well. All right. Now, as I said, because chemistry teachers are both the best/worst, there is zero chance we were ever going to let you get away with having just a 1-part question. So, in fact, I think this is a 3-part question. So, calculate the moles of hexane required to form 150 grams of carbon dioxide. So, if we were measuring this by mass, yeah. All right, so let's talk about that very quickly. So we use mass to measure stuff, obviously, because it's easy. And the mass on this side is exactly the same as the mass on this side. That's because of the law of conservation of mass. And if it's not true, the universe falls apart and we have a bad time. So that's always true. But it's not overly useful. All it means is we know that there's the same amount of crap on either side. We use moles because it's the ratios are important, right? So for example, for every 2 hexanes, we need 19. Why can't I read? For every 2 hexanes, we need 19 oxygen molecules for it to react completely. Otherwise, it just doesn't work. So the ratios are much more important. All right. So let's go back to this. So calculate the moles of hexane required to form 150 grams of carbon dioxide. The first thing it's asking us is we need to know about 150 grams of carbon dioxide. We also need to know the moles of hexane. So there are some steps. First, we need to know the moles of CO2 that's in 150 grams. And then we want to know the ratio of the moles of hexane. Okay, so that helps us work it all out. So first off, moles of carbon dioxide is mass divided by molar mass. We know the mass, and we can look up the molar mass. So the molar mass of carbon is 12.01 grams per mole. The molar mass of oxygen is 16 grams per mole. So that becomes 150 grams divided by, because it's carbon dioxide, 12 plus 2 times 16 grams per mole, which gives us 150 divided by 44. And by the way, that's the fun part. See how we can like scratch out those grams, and the fact that that just means and so that gives us 150 grams divided by 44.01 grams per mole. And all that means is we can cancel out the grams. That's fun, which leaves us with moles. The fact that it's being divided by this up here allows us to convert to straight moles. And that's how that happens mathematically, instead of moles to the power of -1. Which gives us an answer of 3.4083 ... moles. That means that answer goes on. Save that in your calculator. You do not ever shrink it down until the end. All right. So therefore, we look at our ratios, right? There are for every 2 carbons, there are 12 carbon dioxides. Okay. So we can shrink that ratio down from 1 to 6. 1 hexanes to, I don't know what I called that before, 1 hexane to 6 carbon dioxides, and that becomes 1 to 6 ratio. Nice, that allows us to do a little bit of division. So our moles of carbon dioxide, of hexane, our moles of hexane are the moles of carbon dioxide divided by 6. We've got that number over here, right? So we just go pump that in. That number divided by 6 gives us 0.56805. Now, let's go back to our significant figures. This one here has 2 significant figures, only that, right? Really interesting maths question. What that means is, by the way, that this number here, this 150, for our levels of accuracy, is actually anywhere between the number of 145.0001 grams, whatever, right? 145 grams and 144.9999, sorry, 54.999 grams. So our level of specificity is only to these 2. There are ways to signify that you have that over there. Let's put a bar over it or something like that. But we tend to consider that an ambiguous 0. So for significant figures, we only have 2 significant figures, which means that our answer becomes 0.57 moles. Okay. So therefore, 0.57 moles of hexane is required to form 150 grams of carbon dioxide. Yeah. All right, now, as I said, chemistry teachers, sometimes they're the worst. So there's a third part to this question. Third part has actually nothing to do with the second, which is kind of interesting, but it will use information from part A. Determine the mass of hexane that will react with exactly 22 grams of oxygen. So we've got the mass of hexane and grams of oxygen, which means we've got to convert everything to moles and then back again. So we want to go from mass of oxygen, that's 22 grams, into the moles of oxygen. Then we go from moles of oxygen to moles of hexane using a ratio. And then we go from moles of hexane to mass. All right, let's do this. First off, our molar mass of oxygen is 32.00 grams per moles. Our molar mass of hexane, and again, you can add this up, you can look it up, whatever you want, is 86.18 grams per mole. So we'll just keep those numbers there for us. And our first step is our moles of oxygen. We go mass divided by molar mass. So it's 22 divided by 32.00. Again, this gets us our 2 significant figures. That'll be important later on. So we're at 0.6875. Remember, we don't round down until the end. Our ratio is 2 to 19. That's annoying. So it becomes 1 to 9.5. That's much better. Ooh. I've made an error down here. All right, so we made an error. So we get the red pen out because we're teachers. 9.5, which means that one there becomes 9.5. Which means we then do this. Now, it's not going to be that. What it's going to be is going to be 0.07 236 ... moles. All right. So we have to keep changing that number in. All right. So we go with that for the moment. So that's our moles of hexane, and we now need to convert that to mass. So it's a rearranging of the equation to mass equals moles times the molar mass. So again, we're now trying to get the mass of our tone, so we move this one over there by multiplying it, which means you go to the other side. And here we go. 0.07236 ... times 86.18 grams per mole, because that's the molar mass of hexane, which gives us an answer of not that. Hang on a sec, I'll put that into my calculator. Which gives us a mass of 6.2367 ... So it's not far off, but not the same. And all right, as a chemistry teacher, if this was worth 3 marks and I had made that one error there, I would have seen that this is a transcription error here. And there's actually a real chance it would have gone one of two ways. You would have, it stays out of 3, you would have got 2, or you might have still got the 3 marks, depending on how I was marking it. Like, for example, there's a chance you could have made that same error, and I know that the mistake you've made is not, just from looking at it, is not a chemistry error, right? It's not a process error. It's just a simple, you've doofed up I doofed up the transcription of this 9.5 to an 8.5. Like, that's a real simple mistake to make. Like, I can show that I know how the ratio works here. I can show that all this is true. So, I, as a chemistry teacher, probably wouldn't have taken a mark away from that one, as long as all your working out was there. If there's no working out, you get 0 marks for that. So let's now bust it down to 2 significant figures, and that gives us 7.0, but it doesn't in reality. It gives us 6.2 grams. It's much harder to write when the laptop's up this way. I promise that's my real writing on there. So therefore, 6.2 grams of hexane will react completely with 22 grams of oxygen. And these are really useful things to understand if you're talking about industrial processes. If you're talking about doing tests of compounds, we want to know exactly how much so we don't get false negatives, false positives. And yeah. All right, so next to the next bit, structural formulae. They rule. They rule so hard. I love these things. And I think one of the things, I actually find chemistry questions really relaxing to do. Like, I just like to pound them out. It's a good form of meditation. And the reason I think that's the case is because chemistry has some real magic, some real fun, weird stuff happening, right? But none of that's in these processes. These processes are kind of, and naming them's kind of the same, except I'm about to show you benzene, which is a jerk one to try and name. But the processes in them are all kind of, they're the same each time you do it, right? Like, so there's this real sort of meditative aspect. The magic in chemistry is are the concepts, like what's happening with the electrons and the protons on a subatomic level. And you see this with benzene. Benzene's kind of bananas. But as we go on, we'll see that these processes are kind of similar, right? So our structural formula, like, you know, each bond is drawn out. That's nice and simple, really important. All right. Each carbon has 4 bonds, remember that? And we leftover non-carbon bonds are filled with hydrogens. And aside from that, there's a bunch of rules. Like, so propane. Propane means it has a 3-carbon, prop. That's what that means. And the ane means it's all single bonds. So that's our simplest of the ones, right? So we draw a carbon chain in the middle, and we don't have to do anything else with it because it's all single bonds, and we see we've got all single bonds here and here. So there's no point like stuffing around. So now we just fill it up with hydrogens. Boop! That's propane. How good's propane? It's fun. It's rad. Now we move on to 2-pentene or pent-2-ene. Now, these are both ways to draw it. I write the name. This is the way that looks better. This is the way that it should be done, but whatevs. It doesn't matter. It's both the same. You can tell what it is. It's only when it gets like really complex with like heaps of other crap in there, like ethyl groups and whatever, that it gets a bit confusing. That's why we do that. Anyway, 2-pentene. What does this tell us? It tells us it's 5 carbons. That's the pent, like a pentagram, or hailing Satan. It's got a double bond. That's what the ene means, E-N-E. And the double bond, because that's the only thing that stands out, occurs on the second carbon. That's what there's 2 at the front. That's why to be honest, that's why I quite like it in the middle here. So if it's pent-2-ene, pent-2, so there's on the second carbon of the 5 carbon chain, second carbon has a double bond. And you can draw it from either side, whatever you want. I always go left to right because it's fun. All right, so we draw our 5 carbons. Then we'll number them just for making life easier. I've done this in different numbers to show that you can erase that or keep it there, whatever. It's up to you. And then no one's ever going to punish you for having extra carbon, like the numbers on there. And then second one. I don't know why I made that noise. That was weird. So second carbon here, we draw a double bond. It goes between that to that. That's fun. Whoop, back we go. And then we just have to fill it up with hydrogens, which is kind of awesome, right? So this carbon here only has 1 bond off it, so it has 3 hydrogens coming. This carbon already has 3 of its 4 bonds taken up, so it can only have 1 hydrogen. This carbon here, same deal, right? Like it's got 3 bonds filled up, so it can only have 1 hydrogen. See, we put them on opposite sides there. That's because that's what would happen, actually. These hydrogens are negatively charged, but they're positive, but whatever. Their electronegative charge is the same, so they will repel each other, so they'll try and get as far away from each other. And when they're just moving around this single, they can do that. It's cool. Anyway, this carbon here, how good's chemistry? That's my ScoMo appeal. How good's chemistry? Now, vote me out. So here we have a carbon here with 2 hydrogens hanging off it, and that's because it has 2 bonds already. And we're back to here. This carbon only has 1 bond hanging off it, so it gets 3 hydrogens, and that's fine. Now let's talk about benzene. What? Benzene's weird. It's a ring. It's a cyclical one, but it's a special type. It's an aromatic. So benzene's one of the ones you just kind of got to know, right? Because there's rules for it, but they're tricky. So being a benzene, toluene, and all these other fun ones, they have alternating double bonds, which means they don't actually have alternating double bonds. What they've got is they've got electrons in the middle that are just like spinning around off chops, like they just kind of delocalized, and that's kind of sick. Delocalized electrons, which means it doesn't have a home, but it means that it structurally it has alternating double bonds, and it will react as though that's the way, even though they're sort of in between single and double bonds. It's not like, so you've got your carbon, right? You got carbon here, carbon here, carbon here. This carbon has a double bond, this carbon has a single bond, and then it goes around for the rest of the hexagon and crap. But the carbons themselves, like, one of the ways we can calculate is we're looking at the bond length, and the length between these two, this double bond, is longer than a double bond would be. And this carbon single bond is shorter, and it's kind of in the middle, and that's how we know it does that. Now, I could have that backwards, but like as in the length being shorter or longer, because I can't quite remember off the top of my head right now, but that doesn't matter. So let's have a look. Hexagons. So we draw our benzene has 6. So we draw a little hexagon of carbons. Look at this little delightful thing. And then we want to put our alternating double bonds. There we go. There's our alternating double bonds. Isn't that fun? We like that. And now we've got to fill up the hydrogens. The fun one here is that each carbon has... This used to confuse me when I was in university. I don't know why I found this one so hard. I think I just had like a mental block for it. Anyway, maybe it was all the organic compounds that were hanging around and melted my brain. So each one here has 3 bonds coming off it, which means each one can have 1 hydrogen. Boom. And that's it. That's Now, to be fair, that's the way you draw it according to the IUPAC standards. But you'll almost never see it like that. You'll often see it looking like this. which is a better representation, a much better representation. It shows that each one has a solid single bond, but it's got the delocalized electrons in the middle there. Better representation, different representation. I don't know. It just shows different things, right? Like, I mean, to be fair, none of these are the way I represent anything. I tend to only draw skeletal formula because I know enough how to interpret those, and they're better. But each one shows different stuff. This is fun. I hope that was helpful. And yeah, enjoy, and we'll catch up with you next time. Have any questions, put in the comments below, send me an email, whatever you want. If you're the student this was directed towards, call my wife, call me, whatever. Yeah, hope that was helpful, and talk to you next time. Bye now.